Okay, so let's move on to the closing part of this detailed two-day long AM PravaH hands-on course. And so I hope all of you guys, or at least most of you guys, had a good understanding of what AM PravaH can do, what you can accomplish using this piece of software. And I hope you will continue doing the assignments and using it over the course of next 1 week. In the last 15, 16 minutes or so, I would just draw your attention to some of the future visions of AM Prabha and overall vision for this simulation software. The one important thing that we are working on is dissimilar metal joining or multi-alloy, multi-metal sort of additive manufacturing or welding processes. So you can see we have already been able to do that where copper and aluminium they are forming very nice diffused interface, as is the reality in experiments as well. So that is nicely captured. Then gas atomization, I think I briefly touched upon that. This is again something that we have been doing quite actively, and we hope to see more results on that front as well. Very complicated flows where atomization is involved, high speeds are involved, phase change is involved, very severe surface tension effects are also involved. So we are working on that as well. Another very interesting area is wire arc additive manufacturing, where we have taken electromagnetic forces for arc metal interaction. And this is a truly multi-physics solver that we have developed, and this should soon be added to our software as well. Again, more on the data processing side of microstructures. For those of you who understand the textures, they would appreciate that crystallographic orientations can give you different strengths for the same material under different process parameters. And therefore, we have already started working on this crystallographic texture maps, inverse pole graphs for material scientists to be able to get more information out of the microstructure data. This is another very important one, which is part scale modeling. A lot of requests came to us regarding this. So now we are working very actively on part scale simulations where we are just predicting the residual stresses, deformations, and the overall thermomechanical analysis of your entire part. So this is a thin plate, and you can see how deformations and temperature evolution is happening along with the von Mises stresses or residual stresses. And we have been able to do slightly more complicated parts as well. And this is again something that we intend to integrate with AM Prava very soon, which will close the upper end of simulations, which is the real part scale, build scale, end of the length scales. We'll be able to completely close on that aspect as well. At the end of all these simulations, what we intend to do is smart process engineering, where it is not about CFD, it is not about computational techniques, not about AI either. It is the final goal of any of this study is to get you to the right process parameters and help you innovate new materials, reduce wastage, and all the additive manufacturing goals at the industry scale. And to that effect, we are trying to automate the design of experiments process where you define a certain goal that you have to AM Prava, and based on that particular goal, automatic set of simulations will be run for you. The process parameters will automatically be varied based on how close you are getting to the goal, and this will all be based on very advanced optimization schemes so that we are working on and currently working on integrating with the software. Like I said, material properties and process parameter optimization is very important, and material innovation. You can select the most suitable alloy for your very niche area of application using this. Topology optimization has been a very classical problem in the field of mathematics, where you want to retain the strength or the desired properties of a build part while reducing the weight and the mass, because here you're not only making it lightweighted for transportation, you are also saving uh, cost on direct reduction by the virtue of weight reduction. Right? So you by this you minimize the material wastage. You generate lightweight organic geometries which are more close to the real part with which they are coupling, uh, and they have better thermal and structural efficiency, and very ideal for aerospace, automotive, and biomedical applications. Lastly, simulations are computationally intensive. There are a couple of areas that we are possibly going to explore in the future. Now, I've been fortunate to be in contact with some like-minded people on that front, where they're very happy, they're very positive in working together on designing new set of computation physics algorithms that can scale up really fast on CPUs and GPUs, and very ambitious work that may be undertaken in the future is where they intend to design a new silicon altogether, or new sort of architectures that can give very good performance on the existing algorithms. So either we change the algorithms, the way they are written, or we change the architecture of our chips that are currently in the market, or both could be done. So that is one area, and then simultaneously we are looking at adding high performance computing infrastructure, making it command line compatible so that you can run it on bigger computers and clusters. Lastly, we are also developing on unified PravaH knowledge base. We are not promoting just simulations here. We are genuinely promoting PravaH knowledge for high fidelity simulations, for AI predictions, for real time process control and design optimization. So with that, I would like to open this for questions and answers, and very happy to interact in the last 15 minutes with all my team and everyone on the other side, and get your feedback and questions as well about the software, about your ongoing research. Thank you.